All right, these next two videos are really gonna, for those of you who like skipping steps, you're not gonna like the next two videos. They're not bad. They're just a lot of writing. People don't like writing limits, but they're important. If you're not writing the limits, then you are writing lies. Okay? Your writing has to be truthful. It has to mean something. I'll go on a rant about that some other time. But again, make sure you write these limits, and I'll talk more about that in a second. So what happens if we got two infinities and beyond? Ha ha ha. Okay, so the short answer is that look what we can do. Let's assume f is continuous. Well then, do you agree that this is true? Let's not use 0. Let's say any a. Right? This was one of our properties of integrals. And as long as these integrals converge, this is true. Remember, converge just means these limits equal a number. And a can be anything, any real number. A is any real number. As soon as we do this step, bam, it's 3.7.2. Because we know how to find each one of these limits. We didn't do any negative infinities in the video, but it's the same. That's going to be the limit as, I don't know, use your favorite letter. B goes to negative infinity from B to A. That looks kind of weird, but it's fine. Plus the limit as C goes to positive infinity. Integral from A to C, f of x dx. You just write this as two improper integrals, do each improper integral by itself. And I know it's tedious to have two limits. You do need two limits. You cannot, for example, write it like this. I actually really wanted this to be possible. I did, and I didn't remember whether it was possible, so I had to do some research. I really wanted this to be possible, but this does not work. You do need two integrals. All right, even though you might think, yeah, these are going off to infinity, it works out. The answer for why it doesn't work out is very long, and it led me down a rabbit hole, and it won't fit in this video, but feel free to ask about this. As an example, wait, I did have an example. Maybe I deleted it. I think it was 1 over, yeah. 1 over the cubed root of x from negative infinity to infinity is kind of one example of this not working. Of negative infinity to infinity. A lot of times when we disprove something, providing a counterexample is important. This integral does not converge, even though every single one of these is equal to 0. Because it's an odd function. But the integral from negative infinity to infinity, we can't use properties of odd functions about this. We say it diverges. Again, long story. This is our property. Focus on this stuff. But this shortcut doesn't work. Sadly. I was honestly very sad about that myself. Because I also don't like writing a bunch of stuff. But I have to. I got to set a good example for you. I really wanted to say, you kiddos, even though there are a lot of people in this class that are older than me, I still want to say it. Evaluate two integrals here, okay? Integral from negative infinity to positive infinity of 1 over x squared plus 4. Now, a lot of times we just took continuity for granted, but we should really start thinking about continuity for improper integrals. Because in the next video, we're going to show what happens if we don't have continuity, okay? So we do have continuity here. This function, this integrand, is defined everywhere. There's never a time when the denominator is equal to 0, because x squared is 0 or bigger. So we got continuity. That's great. We can write this as two integrals. It's going to be the limit as, we can use whatever letters we want. A goes to negative infinity from A up to 2, up to 0. Up to negative 5, up to pi. Whatever your heart desires. right? When we did this, a can be any real number. You get to choose. You choose. Whoa. How fun. How often do you get choices in mathematics? All the time, but whatever. To choose your favorite number. 0 is one of my favorite numbers. I'm a big fan of 0. That's why a lot of times when I'm grading, I just... Oh, never mind. Sometimes I wonder what percentage of the jokes I make are appropriate for a professor to make to his students. Okay, so it's this integral plus another definite integral. We have to use a different... Actually, it doesn't have to be a different letter as long as it's a separate limit. You actually could use a again. And then whatever you do, I say you get to choose, but these guys need to be the same. Okay, so that the integral combines correctly. And again, it's the same integral. It'll have the same antiderivative. So if you do need to go off to the side to calculate the antiderivative, you can. This one will be a u substitution with arctangent. Again, if u is equal to 1/2 x, I think it works out. That means x is 2u. You can factor out a 4. You know what? Let's just do this one. So du is 1/2 dx. So you get the integral. Let's just look at the antiderivative for now, right? This is 1 over x squared. X is 2u. So this becomes 4u squared plus 4. Oh. And du is 1/2 dx. So we need a 1/2. We have to compensate with the 2 out here. This gives us 2. We can factor out a 4 out of the denominator. 1 over u squared plus 1. And this becomes a du. That's just 1/2 arctangent of u. And u is a 1/2 x. So that's our antiderivative. It can save time to go off to the side. This is the limit as a goes to negative infinity. And again, you do need 2 limits here. I cannot stress that enough. And you do need to write this stuff down. Of, let's see, 1/2 arctan of 1/2 x. We don't need the plus c. It's a definite integral. Evaluated from a to 0. Plus the limit as b goes to infinity of basically the same thing. 1/2 arctan of 1/2 x from 0 to b. That's the limit. I'm already getting sick of writing out these limits. If I can do it, so can you. We could factor out the 1/2 if we want. 1/2 arctangent of 0 minus 1/2 arctangent of a over 2. We're adding the limit as b goes to infinity. 1/2 arctan b over 2 minus 1/2 arctan of 0. Oh, turns out arctangent of 0 is 0 because tangent of 0 is 0. Arctan is the inverse. So that's 0 and that's 0. So what are we left with? We're left with the limit as a goes to negative infinity. The graph of arctan actually really will help you out here. Arctan has horizontal asymptotes at pi over 2 and negative pi over 2. And it just looks like this. It's a sideways tangent. Sideways because it's an inverse function. And inverse functions are basically sideways versions of their original functions. So as a, right, as a is going off to the left, infinitely far to the left, what's arctangent doing? Well, if a is going infinitely far to the left, a over 2 is also going infinitely far to the left. So this arctangent becomes negative pi over 2. And there's still a negative 1/2 in front of it. This first limit is positive pi over 4. Plus This other guy, well, similarly, same logic, go infinitely far to the right on arctangent, it'll approach pi over 2. Multiply that by half. We have 1 pi over 4 plus another pi over 4. We now have 2 pi's over 4. That's pi over 2. This whole integral is pi over 2. Fun fact, you can check your work with Desmos. The integral from negative infty to positive infty of 1 over x squared plus 4 dx, is that pi over 2? Heck yes, it is. All right, I took off my glove. I don't know why. It's like a half glove, so I don't smear my tablet. Anyway, checks out. We're good to go. All right, let's do another one just for practice. Part B, the integral from negative infinity to infinity of x e to the x dx. So again, this is easy. It's going to be the limit as a goes to negative infinity. I don't know. Let's use different letters. I love different letters. All right, I don't love different letters that much. B, I'm not very creative. Of b to 0, choose any number you want. I chose 0 here. Doesn't matter what number you choose. Plus integral with a limit in front of it. As c goes to positive infinity from 0 to c of x e to the x dx. And now we need the antiderivative. Well, it's usually helpful to go off to the side to find this antiderivative. That way you don't have to write the limits 50 times. Nobody likes doing that. What is the antiderivative of x e to the x dx? Now this is another example, by the way, of, I said there's a counterexample. Why you need to use 2 limits. This is another example because this is also an odd function. So from negative a to positive a, this integral is 0. But we can't just say that this is not an a. This is not a number anymore. We can't just call it 0. And I know that's not a great answer. It just takes too long to explain why in this video. All right, so let's get to it. We have to use integration by parts. Okay, this will be our u. This will be our dv. U is x. dv is e to the x dx. du is dx. And v is the antiderivative, e to the x. Integration by parts says that this is u times v minus the integral of v du. Oh, I like the antiderivative of e to the x. It's just e to the x. So this antiderivative is just x e to the x minus e to the x. Nice. So this will be the limit as b goes to negative infinity of x e to the x minus e to the x evaluated from b up to 0 plus the limit as c goes to infinity of x e to the x, that same antiderivative, evaluated from 0 to c. Now, look at this. This is the limit as b goes to infinity of, well, when we evaluate 0, this first guy is 0, minus e to the 0 is 1. Subtract when we plug in b. b e to the b minus e to the b, plus this other limit. Let's just look at this first limit before we go on. Right? Look at this limit right here. The limit as b goes to infinity of, we can worry about the negative or not worry about the negative. Let's just look at the part in parentheses. b e to the b minus e to the b. Again, that's infinity minus infinity. So we're going to factor and e to the b out. We're left with b minus 1, just like before. They're both going off to positive infinity. So this whole thing is going off to negative infinity. It doesn't even matter what else is here. We know it diverges. Okay. So in this theorem, we can only do this if they converge. Okay. So these guys right here are going to diverge, and that's our answer. It diverges. Like each one is kind of going off to infinity, even though if you look at it graphically, right, this is x e to the x. Wait. I said this was an odd function. It's not an odd function. One of them goes off to infinity. The other one is actually defined. I'm crazy. Okay. So wait, where are we? Yeah, here we are. So the second one. Oh, I see what happened. I lost my negative here. This one actually converges. This one converges because b is going to negative infinity. This converges to 0. Right? They both go to 0. This one's kind of hard to see where it goes to 0. Because technically this is 0 times infinity. You have to use L'Hopital's rule on this one. But it doesn't matter that this converges because the other one diverges. So this first one converges. But if you looked at the second limit, that's going to do... The second limit is the calculations that we did the original time. Okay, so that's the same... I'm not going to redo it because these same calculations hold just with the c integral to show that the second one diverges. So even though this first one converges, this first part's a number, the second part goes off to positive infinity, so the whole integral diverges. All right, so made a mistake, but have corrected it. Don't drop your negatives, everyone. And then, yeah, that takes care of that. So again, to the left, yeah, it does converge. To the right, definitely not. Let me know if you have any questions, and bye-bye.